Hey, I think we should get started. Welcome everyone to Physics Club. So today it's a great pleasure to have Roger Melko to give the Physics Club. So a little bit about his academic trajectory. So Roger got his PhD from UC Santa Barbara in 2005 with Doc Scalapino. And then he spent a couple years at Oak Ridge and then moving to University of Waterloo, where he has been faculty ever since. He's also affiliated to Parameter. So Roger is a world expert in computational quantum many-body physics. He has made numerous seminal contributions. So he pioneered the computational study of entanglement entropy in quantum many-body systems, spin models, which has grown into a much bigger subject later. And then he switched mostly to machine learning algorithm, their applications in, again, in many-body systems. And he has been at the forefront in that subject. And I think that's what he's going to tell us today, large language models for quantum simulations. So without further ado, Roger, please take it away.
Thank you very much. Is this microphone projecting at all, or is it just online? Can everyone hear me? Thanks for the intro. It's my first time to Yale. Everyone's so nice. That's all I'll say about that. But no, it's a pleasure to be here and to talk about language models, which are a form of machine learning, which I'll kind of loosely define. And yeah, as Meng mentioned, I'm a condensed matter theorist, so apologies on that front. You'll see it polluting some of the way that I think as I go into the talk. And I guess I've drifted over the years from strong correlation physics, like strongly correlated condensed matter systems, kind of into entanglement entropy and quantum field theories. And I continue to drift into quantum simulation, which I'm going to loosely define as quantum computers doing interesting things for simulation. But at the core, I work on computational algorithms. So very much a computationally inclined research group up in Waterloo. And I see this as all a continuum of a continuum of the same topic. I don't feel like I'm switching around a lot, but it kind of looks like it on the surface. The machine learning effort in my group very much started with Juan Carrasquilla, who was a Perimeter postdoc back in 2013. And by 2013 was an interesting year for machine learning, because that's when the convolutional neural network, what was it called, AlexNet, came out and won the ImageNet competition. Basically, roughly out of Jeff Hinton's group in nearby Toronto. And I was telling the story today, but Juan and I and some other Perimeter postdocs, we'd work all day on condensed matter and field theory and so on. And then at lunchtime, we'd sit around and talk about machine learning. And at some point, I was like, why don't we just start working on machine learning? And so Juan and a few others at Perimeter kind of seeded, I think, a lot of the work that I'm going to talk about today. But in particular, the language models, so what I'm calling generative models and language models, kind of came out of our efforts, just serendipitously in this paper back in 2018-ish, when we were trying to essentially do tomography on POVM states, which won't talk too much about, but for a measurement technique in quantum physics. And Juan came to me and said, these recurrent neural networks, which come from language, are beating any of our other architectures. And long story short, that's, I just quit listing papers, but we had all, initially many different efforts in kind of leveraging these language models to do tasks in quantum mechanics essentially came out of that, including some PhDs. Mohammed Hibet Allah, who was a co-advised PhD student. Now he's teaching faculty at Perimeter. Giacomo Torlai, who I'll mention several times, pioneered a lot of our generative model work. He's now working on the control stack of AWS quantum computing, the thing Oscar Painter's building in Caltech. Too many names to mention here. One that we were talking about, Matthew Radzahovsky, who is young, Leo's young son. I don't know why I said young, but who's now working at MIT on these and similar topics. So it's been a very interesting journey with my students, and they've really taught me a lot. And so, everything that I'm going to tell you today has really come out of my students and postdocs, pushing and pulling me in all sorts of different directions. So just briefly, 2 points on an outline. For the generalist, let me focus on a few points to do with generative models, and specifically what I'm calling a language model, which I'll define several different architectures, including the famous GPT-like transformer model, which I'll talk a lot about. And then in the second half of the talk, if I have time, I'll probably be rushing through this. I'd like to talk more about how we apply them in my group to problems in quantum simulation, which I kind of have a specific definition of, the quantum simulation and beyond. And this is the MOT. It's one of the components of QEra's neutral atom Rydberg array quantum computer up in Boston that we do a lot of work on. So I'll talk much more about that. But first, generative models and language models. So we very much entered the or a age of generative models in artificial intelligence. I through a simple kind of way of organizing thinking around generative versus discriminative architectures, but really it's more of a generative versus discriminative setting for machine learning. Discriminative means classification. If we're talking about ImageNet, 2013, deep neural networks, deep learning, convolutional neural networks. These are tasks where you feed pixels from an image into a deep network, and then at the other end of the network pops a label. That's a cat, that's a dog, that's Obama, that's Trump, whatever. It's a discriminative model where you're kind of identifying what's in the image from the pixels. A generative model is a model where you could generate maybe those same images back. You could generate images on the internet of celebrities or of faces of people, or it kind of depends on what you've trained these things on. But it's just the idea that you're actually generating new instances from an underlying probability distribution. You'll see a lot of work coming from generative models today in images, and I'm not going to talk about those architectures, but they're very closely related to normalizing flows, diffusion models, stable diffusion. And one of my favorite is Midjourney. So if you want to generate an image of a stormtrooper family in the style of Norman Rockwell, you literally give Midjourney that prompt. That's the prompt that you type into this program Midjourney. That's one of the images. And these are really remarkable. I just really love looking at generated images on the internet for some reason. These and other diffusion and other types of models actually have their origin very much in kind of statistical physics literature and statistical physics ideas that came largely from Hopfield models. So John Hopfield in 1982, I think, published the famous Hopfield network, which is just a fully connected Ising model. And the learning that occurs in a Hopfield network is learning the interactions of the Ising Hamiltonian. These were developed further in the early 80s by Jeff Hinton and other people into the restricted Boltzmann machines, which are actually a very widely used architecture now in many-body physics, and again led to some of these, in some nonlinear way, these current generative models. But really, I point them out because of an interesting feature, and I'll talk more about the specifics of a restricted Boltzmann machine. But the fact that they're based on an energy function. Okay, so an energy-based model is really a model. It's a generative model where you define an energy, which is a Hamiltonian that connects, a whole bunch of Ising nodes, if you will, or Ising variables, but also is normalized with the partition function in the usual sense. But through that is used to define a probability distribution. So if I wanted to generate an instance of this picture from an energy-based model, somehow I'm trying to encode the distribution of all possible stormtrooper, images on the internet or something like that. Okay. So the idea is that there's a probability distribution that underlies this. A language model I'm calling a subset of generative models, and it's a loose definition, but language models generally are tasked with some sort of language task which involves a sequence. And so here's an actual something I just ran on a GPT-3 model online. I think it's, if you go to talk2transformer.com or something like that, there's a trained GPT model from a few years ago that does text completion. But I believe text completion is kind of the quintessential language model task. And so what I entered into this is hickory dickory dock, the mouse, complete my sentence, please. And what the generative model did was complete the sentence with everything in the green. And you can see what's going on is that, it did pretty good at the start. And if you run it and ask it to generate more and more words, it starts to drift off into some sort of crazy space. But what this model is doing is really probabilistic in the sense that it's trying to predict the probability of the next word in a sequence. So again, that's kind of the quintessential role of a language model. Most language models these days are based on the autoregressive property. So they differ from the energy-based models in that they don't have a Hamiltonian internal to them that parameterizes the distribution. In some sense, the task is still the same as an energy-based model. You want to learn the probability of, of the next word in the sequence given the previous word or something like that. But instead of using an energy function and a normalization through a partition function, what these models use is the autoregressive property, which is just the chain rule of probabilities. And this becomes important later in my talk. But the full joint distribution over all words in this sentence turns out to be the product of the conditional distribution of word I, conditioned on everything previous to it. And, the important difference, why did I put this on the first slide, between the generative model, the energy-based model, is that there's no unknown normalization in this. And so models based on this autoregressive property are implicitly normalized through all these conditional distributions. And I'll talk about why that's believed to be important. But this property underlies recurrent neural networks, which until the advent of transformers were really the best language models out there. Long short-term memory, gated recurrent units, LSTMs and GRUs are famous RNN architectures. And these things cracked open a lot of language problems, including translation and other things like that. Now they've been eclipsed by the transformer architecture, which I'll talk more about, which underlies the generative pre-trained transformer GPT models, which OpenAI and other companies develop. And you probably use, if you use Chat GPT, you're using one of these autoregressive transformer models. So that's kind of just a very broad overview of how I'm placing discriminative, generative, and language models in the broader landscape of AI. So, questions on there? Yeah.
Capital N.
Pardon?
The capital N, who determines the depth? From I equals 1?
Oh, it's N is, yeah, sorry. I don't know. That's going to be my number of qubits soon. But N is the number of words in this sentence. Yeah. So this is a sequence of words here. Yeah, so I think I'm going to answer that in a minute. So GPT, of course, why are we all talking about GPT? It's because it's exhibited what I'm going to call emergent abilities. And I really like, if you haven't read it, the technical report for GPT-4, which came out less than a year ago, right? Really shows lots of interesting things, but one of them I really like is the exam results that you feed in a prompt and it gives you an answer for all sorts of, I guess, American AP type exams, including physics somewhere here, chemistry, and so on. And there's a huge jump in performance between GPT-3 and GPT-4. And you can see it in the difference between the blue and the green bars. And so something happened along the way between GPT-3 and GPT-4, where the AP chemistry results went from a 20% to, whatever, basically 80%. And, especially relevant for here, GPT scores would be in good position to be admitted into Yale. So at this point, OpenAI can produce an AI bot that could be admitted into this very university. So something's happening, something very interesting is going on in this realm of generative language models. And sort of, I think the point of this talk is we like to harness this for physics applications, but first we have to understand what's going on. So to understand that, let's just go back to basics and we think of those P of X's, those probability distributions that I showed. And what is the basic setting for a generative model? So the typical setting is what we call density estimation. And again, what we're trying to do is take data, which is represented by these vectors here, which is sampled from some black box. It could be the internet, could be all images of cats and dogs or stormtroopers on the internet, or it could be a black box that's some physical system. For me, it's going to be a quantum computer. And I'm measuring, projective measurement outcomes of qubits, and they're producing a sequence of ones and zeros. And to answer that question, n is the length of each one of these vectors. Let me in the qubit language, you have n qubits in your black box, and you're producing a projective measurement 1, projective measurement 2, 3, separate instances up to as many measurements as your budget allows you. So either that's as many pictures of stormtroopers as on the internet, or as many shots as Misha Lukin will give you out of his device. And we use this data to train parameters in some model with the goal of learning P of X in the black box, okay? What is the model when we talk about GPTs and models and all these types of things? Really, they're just a bunch of real numbers, a bunch of parameters, and you can think of them as a neural network. You can think of them as a deep network, but inside all of these different parameterizations is basically just real numbers. And we're trying to learn a set of parameters, and I'm calling them lambda, okay, such that the goal is that our parameterized representation of the probability distribution is as close as possible to whatever's in the black box, right? And once we've done that, then our goal for training would be complete. If these two functions were the same, then we would have successfully trained a model to represent the black box. It's done through a loss function, and there's many different ways of defining loss functions, but the simplest way to think of a loss function for this goal is to look at something called the Kullback-Leibler divergence for the experts, or the relative entropy, I believe it's called, which just involves taking the expectation value of the log likelihood of the model, the parameterized model, with respect to the data drawn from the black box. Okay, so that's just what I would call a estimator for an expectation value of log P. And so what this loss function lets you do is simply take these raw ones and zeros. You just simply take the binary counts, and you can form a loss function based on the structure of your model, and then use something like gradient descent to optimize all those parameters. And it's as simple as that, really. And of course, the devil's in the details. But a lot of what we're doing in this type of machine learning is defining a very complicated loss function and then trying to solve that optimization problem in some clever way. And so I think the philosophy of solving optimization problems, or recasting all sorts of problems into these highly non-trivial optimization problems, and then finding a good local or a good global, the best global minimum, is kind of the philosophy here. So back to maybe a more physics perspective. What are the models that we use for this type of setting, and how do they relate to what's out there in industry? And I mentioned the restricted Boltzmann machine as an example of an energy-based model, because again, it was really a pioneering architecture, both in deep learning and also in whatever the field of condensed matter physicists working with machine learning is called, which kind of started in 2016, 2017. And the reason is it's a very intuitive model for physicists to train and to work on. So a restricted Boltzmann machine is just an Ising model. So you have variables that are zeros and ones, and we divide them into two different layers. One is visible and one is hidden. And the visible layers, if I'm thinking about n, that number, there's n visible units on the left-hand side here. So if I have n pixels in an image, or if I have n qubits in my quantum computer, I have n visible units here. And on the right-hand side is what we call the hidden or latent space. And it's an important concept for machine learning because it's variable in size. So if I want a more expressive model, if I want to represent more complex probability distributions, I can vary the size of my latent space here, either make it bigger or smaller, okay? So what making it bigger does is add more parameters. And the parameters of my restricted Boltzmann machine are weights and biases. Weights which occur as connections between hidden and visible, and biases which are like local fields or something like that. So again, here's my energy-based model. There's my model energy, which is this Hamiltonian. Here's my Ising interactions between visible and hidden only. Visible and hidden only is important for training, but you could also have connections within the layers if you wanted. And here it looks like I have some sort of symmetry breaking longitudinal fields for the visibles and the hiddens. Those are all my parameters. Again, what I'm doing is I'm defining the model, and then I'm marginalizing over or tracing over the hidden space to get just the visible values of this. And that's what I take and put in my loss function and so on. So the important part of an energy-based model, one important part is the fact that I don't know the normalization. So if I want to sample it, I have to sample it with some sort of Monte Carlo-esque technique. So Markov chain sampling is kind of the typical way of doing this. And one important part of Markov chain Monte Carlo sampling is that in the generative mode, so once I train it and start generating new instances, is those instances are correlated to each other. And anyone who's done single spin flip Monte Carlo in the Ising model knows if you flip one spin, that configuration isn't all that much different than the one where you haven't flipped that one spin. So this intrinsic kind of concept of an autocorrelation time occurs, and which means your sampling is never perfect in these models. So that's in contrast to the autoregressive models, which underlie a lot of the large language technology that we see today. They're harder to draw, but I'm going to show you what's in that green box. But again, I guess the strategy for an autoregressive model is very much a sequence-based strategy where, you know, here's my visibles in some sense now. I'm putting in, you know, this is one qubit measurement or one pixel for my image. And then I'm outputting the conditional probability distribution of the next X in the sequence. So you see how it makes more sense for language if I'm thinking about these being words and I want to probabilistically ask what is the next most probable word in the sequence, right? The beauty of the autoregressive property is that if you can make each one of these conditional distributions normalized, then the joint distribution that comes out is also normalized. So there's no partition function. Seems like magic. The generated samples, therefore, can be done IID. So you can produce perfect independent samples from an autoregressive model without this autocorrelation time or this autocorrelation function. However, the downside, if there is one, is that everything has to be mapped to the sequence. So again, it's very natural for languages, but in some problems that we deal with, it might not seem all that natural. So again, just contrasting two different. You have a question?
Can you repeat why the samples aren't correlated if I generate them in sequence?
I'm just trying to think why are they uncorrelated? If what?
I generate them in sequence.
Sorry. The samples along the sequence are correlated, but once I do an entire joint distribution P of X, that I've sampled all N of them, then the next time I do the sampling, those two are uncorrelated. So if I look at this picture, if I was generating these from the generative model, X1 and X2 would be uncorrelated. Whereas in the Markov chain, that's not true. Yeah. Yeah, good question though, good clarification point. So the point of the sequence, you know, I think really becomes important again in languages, but if we can map any problem to a sequence, we can use an autoregressive model. So on the left-hand side is an autoregressive model for hickory dickory dock. You know, the next word, it's obvious, you know, here I sample from a dictionary of size 1, 2, 3, 4, 5, 6, 7. You know, my first word is hickory. What is, and you know, my second word in the sentence condition on the first word. You know, if I sample dickory, then what is the third condition on the first and second, and so on. That's how an autoregressive model works. And you know, the question is how strong, you know, how strong of a correlation, you know, can you keep within this green box as your sentences get longer and longer? What I'm going to show you in the second half of the talk is mapping spatial, you know, coordinates of qubits to sequences. And so it's the same point, except my dictionary is now only 2. There's only 2 words in it, you know, spin up, spin down for a qubit, or more words for a qudit or whatever. But you have a very significantly reduced dictionary size, but you can have very highly non-trivial correlations that come from entanglement and all sorts of other stuff. And the point with the, you know, the qubit case is when I get the joint distribution over all these P, as long as I have phase information, which I'll talk a little bit about, I really have the wave function as being the output of the autoregressive model. So that's my mapping very generally between, sequences and language and so on, and, output of a qubit device, which we'll see a lot more of. I promised to crack open the green box of an autoregressive model, but it's not all that pretty. Unlike the RBMs and the energy-based models, which I believe are very intuitive from a statistical physics perspective, a lot of the language models were, heuristically built based on all sorts of nonlinearities and forget gates and things like that. But basically, architectures have converged in two different cases of interest. So the first is a recurrent neural network, which before the GPT type transformer models, again, was state of the art for language tasks. So this direction is the direction of my sequence. So apologies, I swapped out X with sigma. So I'm imagining qubits, I guess, here. And inside each one of these green boxes is what they call the recurrent cell. And so they're named recurrent neural networks because you can have the same parameterizations within each one of these green boxes. So they can only be, there can be only one of them and this thing will still work. What's going on in a recurrent neural network is you're passing a hidden state. So this idea of a latent space or a latent, encoding of your information is encapsulated in what they call a hidden state, which is passed between occurrences of this recurrent cell. They're typically initialized, and let me just go maybe to sigma 1. So here's the x1, here's the first word that I've sampled from my dictionary. It goes into this recurrent cell with also a hidden unit, which you don't have to interpret, but what happens is the green cell outputs the next instance of the hidden unit. So given, h1, I output h2 based on some nonlinear function that has some weights and biases in it, and also, takes, the consumes, if you will, the sample that I've produced from my dictionary. So there's this highly nonlinear function. It doesn't really matter what it is, but the parameters occur within it. So the weights and biases are parameters. Further up in the stack, there's a softmax. So basically, a softmax gives you a normalized output. So your conditional distributions are normalized, which is the y's. And then those y's are sampled to give you the next occurrence, sigma 2 in the sequence, which is then fed down into the next recurrent cell and so on. And what results if you combine all of these sigma 1 to sigma n outputs is that one complete sample sampled from the joint distribution of n qubits or n pixels in your image. And when you perform this the second time, left to right, you get a completely independent sample that doesn't depend on the first sample. So it's ugly and it doesn't look like a restricted Boltzmann machine, but it's a very powerful architecture. And just aside, you're wondering, how is this a talk about quantum physics? It's very simple to attach a phase to these outputs. So you can basically manipulate the phase or the hidden unit with a soft sign, and you can basically accumulate phases and parameterize both the wave function, amplitude, and its complex phase. So there's some interesting points that have to do with the phase, but I won't really talk too much about it in this talk. So what's, I guess, the challenge when you're going from languages to qubits in a spatial array is how the correlations are encapsulated, within the recurrent neural network or whatever the sequence is. And again, it makes a lot of sense when you have hickory dickory dock, and these hidden units are now tasked with what they call the context in the language models. How much does what I'm saying now depend on what I said previously? How long does that context have to go back? How many words do I have to retain information about the context? For physicists, that's literally correlations. How many correlations occur between, whatever x5 and x1 or x1000 and x1 or something like that. So when we think about physical systems, where it's much less obvious that everything is a sequence, and just to belabor that point, here's a two-dimensional array of qubits. If I want to use an autoregressive model to model the wave function, I have to define a sequence. But then my sequence has very sort of long, contexts between, say, qubit 1 and qubit 6 here or whatever, right? So I have to, make sure that I pass hidden units as much as I possibly can in order to relay that context through these physical variables. And each time I pass a hidden, a hidden vector, through one of these recurrent cells here, it goes through this nonlinear function. And you have to worry about whether or not you do that repeatedly, whether or not you degrade the correlations and so on. So the most general recurrent neural network that you can do is essentially pass hidden units between everything that occurs previously in a causal sense in your autoregressive sequence. So the red is the autoregressive sequence, right? And the black is the hidden units or the hidden vectors or the hidden information that I'm passing. And so the point is that in a recurrent neural network, you can only pass these things forward. If I want to sample the probability, the conditional probability of qubit n, I can pass information forward but not backward. So there's some causal structure to these things, which is sort of non-obvious in terms of how I define that sequence. Or another way of saying it is that sequence is arbitrary. And so is there a way that you can screw this thing up by not picking the right sequence? So that's a general issue with autoregressive models. Transformers, in some sense, are more powerful in the sense that they've solved this problem using the attention mechanism. So anyone that uses a GPT type model is basically using a transformer now. Things are getting progressively more ugly. As I went from restricted Boltzmann machine to RNN, now to the transformer, I mean, God help you if you're trying to figure out exactly what's going on in this architecture. But the basic point, which I've boiled down here, is that there is essentially a structure of correlations that's all-to-all connected. I should say it connects pairwise, with between every single node in the sequence. So there's still an autoregressive sequence typically defined in these models, but what they have is what they call an attention mechanism. And the attention mechanism, unlike the previous slide, retains all possible correlations. So really, in some sense, what you're learning is the strength of these correlations within the masked, so-called masked self-attention unit. And when you go to use that autoregressively, you just mask the ones that are ahead of you in the sequence. And so I'm trying to find a description of transformers that give you the intuition that they're more powerful than recurrent neural networks here. But I'm not even 100% sure this is completely right. Nobody knows why these things scale better, why they're more powerful. But there's definitely structural differences within transformers that make us believe that they retain correlations much better than recurrent neural networks. So I'm not going to talk too much about the internal structures of these things more. I hope that was kind of an interesting overview. Happy to take any questions on the structures, but unless there's something pressing, I just wanted to point out that the reason we're interested in transformer models is they've really, I think, blown open the attempts to scale these things up. And so they've scaled to millions and trillions, or I don't know how many parameters these days. And they've also displayed what we call non-trivial emergence in some context. And so there's a couple interesting papers I just put up here from the machine learning literature. But a language model becomes a large language model at some point when it has a lot of parameters and has used a lot of data and a lot of compute to train it. And the striking thing about large language models that's come out in the machine learning literature is somehow the bigger they get, the better they get, which is kind of counterintuitive if you think that more parameters means that I have to have more data, and I have it's like if I'm fitting a polynomial and I only have so many points or so much data, the lower the order of my polynomial, the better. This is counterintuitive in transformers. So the more parameters I have in my model, the more weights and biases, the more the better these things learn in the sense that they have a lower total loss for the same number of tokens, and tokens is just words that you're sampling from the dictionary. So this is again, if you have 10 to the 3 versus 10 to the 9, 10 to the 9 seems to train better on this, has a lower loss on the same number of tokens as 10 to the 3. So something about scale in transformers benefits. And also, there's emergent properties that are hard to define what emergence is. I've used, from the second paper, a definition of emergence here, which is credited to, the machine learning practitioner Steinhardt, who then also credits Phil Anderson, who we know well from more is different. So this is really the more is different explanation of emergence. But how this occurs in large language models, and here's some tasks, modular arithmetic, I can't remember, some translation, some blah, blah, blah. There's all these different, here's Lambda, open source model, here's GPT-3. Here's the accuracy as a function of training floating point operations, okay? So it's not flops, it's flop. But as you put 10 to the 23 or 10 to the 24 flop of data into these models, you see some sort of non-trivial emergence in the accuracy. So it's kind of the basic definition of emergence in these things. And it's very poorly understood, I'd say, what causes these things to have emergent behavior. But anyone who's used GPT-4 or ChatGPT, can see that this threshold has been crossed where, these large language models are doing something that smaller models don't seem to be capable of doing. And so I think the difference between GPT-3 and GPT-4 in terms of their emergent abilities was, I think, very striking. So I'm going to go on to the quantum part, and I'm going to speed up. But I could end the talk here if I wanted to. So I'm just going to put a bit of a discussion before I get into the quantum part. So language models, breakthroughs have occurred, and it's typically three things. Parameterization, so the number of parameters in the model has gotten large. GPT-4 contains 1 trillion parameters, and there's bigger models now. It's big, but it's still not that big. You can fit a trained model on a USB stick and pass it out. So in that sense, they're like a Pandora's box. If you train them, you know what I mean, they can be distributed fairly easily. So the difficult part's the training. That comes with 2 points. It's data. How much data can you scrape off the internet? Now the entire internet's been scraped by language models and has been turned into tokens for training. GPT-4 costs $100 million to train. That's just GPU time, and basically use the entire internet. But also it's a function of compute, because that data is all put into a bucket and it's pulled out probabilistically, trained, thrown back in, pulled out many different times. Each one of those training cycles is called an epoch. And again, it's Avogadro's number of floating point operations has now occurred inside of these models. So the combination of parameterization, a huge amount of data, and a huge amount of compute, these things have all conspired to give us the emergent abilities of language models. And so I think my question for myself is, are language models posed to make breakthroughs in other fields that aren't just, I don't know what, stormtrooper pictures or whatever, and I think really central for us is scaling of quantum computing architecture. So we want to build quantum computers to achieve tasks, that classical computers can't do, but we're faced with many scaling problems. I would argue many scaling problems in their control and design and so on. And so, can language models help us? If we want to build a simulator, like a quantum simulator to demonstrate emergence, can a language model do the same thing? Can we have an emergent language model that gives us kind of a digital copy of a quantum computer and does the same task? Or can it help us create that quantum computer, through, I guess, unique control structures and so on? And if we do so, if we use language models to if we leverage them for quantum simulation and quantum computing, are we losing something in terms of interpretability? Because we really don't know how, conventional language models work. So we use them to design, say, a quantum computer. Do we really know how that quantum computer works? So I think there's lots of questions that are opened by this field. And finally, can we afford to do this in the sense that, none of us have $100 million to spend on training large language models for a digital copy of a, quantum computer. And should we spend the carbon to do this, I think, is another point. So these are very much economic questions in as much as they are science and engineering questions. Maybe I'll take questions here if you have any, because I'm going to delve into quantum physics and go pretty fast now. I'll come back. Okay, go ahead.
What's the ratio of costs between training and evaluating one prompt for the language model?
Training is all the cost. Inference costs almost nothing. So it's all training. So once you train a model, pass it to your friend on a USB stick, you just plug that in here and you can prompt it and blah, blah, blah. So inference costs almost nothing. So it's all training.
Why?
Oh, question online?
Hello, I have a question about the sequential ordering you mentioned before. So based on my understanding, the sequence ordering only comes from the position embedding, right? If we remove that, the transformer or the language model can actually be like permutation invariant. Is that true, or how will that help us?
Somebody help me with that question. Did anyone understand it? Maybe just ask the kernel of the question again.
Oh, okay. So I'm just wondering, you mentioned one of the shortcomings of using transformer or like language model is that, or like it's like they are sequential and they require like an ordering like a natural language. But actually that only comes from the fact that we add the position embedding to the transformer, right?
Right. Yeah, I have the positional encoding, you're right.
Yeah, so if we remove that, that will actually be permutation invariant. It doesn't care about the sequence of input, right?
Right. You're right. You can make a transformer model that isn't autoregressive if you remove the positional embedding. Yeah. I don't know if there's any comparison of performances actually, or performance between the non-autoregressive and the autoregressive transformer. But you're right. Yeah. So I didn't go much into the architecture, but the sequence read is defined at some point necessarily, I think, here.
Okay, yeah, thank you.
Okay, in 5 minutes, I'm going to go through 20 quantum computing slides. So open your eyes. No. So I just threw a bunch of things together here because I thought, depending on how much time we have, this is where I tell you what I'm doing with this stuff. So I'm really interested in data acquisition rates from today's machines and how we leverage that data. Number one, again, to, do tomography or to understand what's going on inside of these computers. But number two, to help design the next generation. So I think we're bootstrapping quantum computers here, and we're asking if language models can help. So very much data driven. I don't know, I put a few of my favorite architectures and the data acquisition rates. And actually, I'm not sure I got the superconducting circuit correct, but is it roughly right? 10 to the 7 shots a second. It's the fastest anyway, right?
10 to the 6.
10 to the 6, 10 to the 7. These are incredibly fast in terms of their time scales. Compared to the atom devices, so the trapped ions, the one we have in Waterloo is giving us about 200 shots a second. And my favorite architecture, which is the neutral atom one, actually is very slow. It's about 1 shot a second, or depending, it's very size dependent, for 256 qubits in QEra's machine. And I just got to put this picture of me here because they let me in the lab. This is my student Roger. So this actually gives you about 3 shots a second. So, contrary to what I said, in some sense, we're data limited for a lot of these quantum computers. And so one task that I'm interested in is whether or not we can leverage this limited data in order to do some of the things that I'm interested in terms of machine learning. Okay, so let's see. I want to talk about Rydberg atom arrays mostly. So that's the one on the neutral atoms. So Rydberg atom arrays leverage optical tweezers. The MOT, the magneto-optical trap here, is used to basically spray, rubidium into a vacuum chamber that has optical tweezers, and by with some probability, an atom is trapped in those tweezers, and then it's used as a qubit in its electronic configuration, where the ground state is 0 and the Rydberg state is 1. And there's all sorts of interesting technology that we can leverage to turn these things into interacting qubit systems. Basically, this Hamiltonian. So this Hamiltonian is what they call the blockade Hamiltonian, where I have, basically, here's what I said: the qubit encoded in the ground state or the Rydberg state, and a Rabi frequency, which gives you transitions between the two. So that's your off-diagonal matrix elements come from that. And you have a detuning, which is like a longitudinal field or a chemical potential. And then you have long-range interactions, which are like van der Waal type 1/R6 here. And I'm in the occupation basis. And so the Hamiltonian is diagonal in N, which tells me the Rydberg occupation basis And for the experts, this implies this. Oh, I got the sign wrong. But if the sign was negative here, this implies that the Hamiltonian is stochastic, which simplifies a lot of things in terms of the wave function. The beauty about Rydberg atom devices is they're very coherent. They have long time scales. They have very low noises. But the downside is just what I said. When you throw in atoms from the MOT, there's only a finite probability that they get loaded into the optical tweezers. And so part of the compiler stack developed by Manuel Endres in Misha Lukin's lab is to rearrange these things physically by moving the tweezers together that are close, then letting them time evolve under the Hamiltonian, and then doing a single shot readout, which blows the Rydberg atoms out of the tweezers, and you have to go back and start again. That's a very long time scale. And this is data that we've acquired from QEra's machine, which it's hard to see here, but you're getting 3 shots a second out of this procedure. So that's basically why these are data limited devices. When you have limited amounts of data, models help you. And very simply, if I wanted to parameterize, if I had data and I had enough data to fill up a distribution, I wouldn't need to parameterize it. But if I did parameterize it, which is my red function here, I can leverage a lot less data to get good information out at the cost of what they call an inductive bias. So any neural network has a bias depending on how you form it. But I guess what I'm saying is that bias is good, and there's some evidence that I won't talk about. So here's, I really got interested back in 2017 when Misha's group put out this experiment of a one-dimensional atom array. And it had an interesting quantum critical point, if you will, between a disordered and an ordered region, which is accessed by the detuning. So we did a lot of work on reconstructing that state near that phase transition. And here it is. There's the occupation going from 0 Rydberg occupation as a function of that symmetry breaking detuning into, I guess 0.5. And you can see part of the array going from everything in the ground state here to everything, to a Z2 state here, which is Rydberg. It only fluoresces in the ground state, Rydberg ground state. And what we did was we took 3,000 shots for 8 or 9 atoms, 8 atoms, and reconstructed in almost a tomographic sense the wave function from this experimental data. And so we get really good correspondence. In this case, it was a restricted Boltzmann machine between the experiment. And in this case, we have exact diagonalization that we can use to confirm the experiment. But an interesting thing occurs because when we have a trained model, just like a variational Monte Carlo simulation, I can do a whole bunch of different estimators, including off-diagonal expectation values and even entanglement. You can do Renyi entropies in the trained model. And so what this gave the experimentalists is another window to access off-diagonal quantities from which we find a lot of discrepancies in the original experiment. By the way, this never gets published. I hope Misha's not listening. No, but this is kind of the feedback that we would love to have with experimentalists, is when we see discrepancies from what they're trying to build in the data. Actually, they went back and fixed something in their control parameters, which I think demonstrated to me a lot of value in this approach. Long story short, we've been doing the same type of thing on 2-dimensional arrays now, which are available through the QEra device and also Misha's lab. Here's a similar phase diagram, but now mapped out experimentally in the 2D array, where you go from a disordered regime to what Sabir tells me is the first instance of the 2+1 dimensional Wilson-Fisher fixed point in an experiment, if you can believe it, which is this kind of this lobe here, into a checkerboard state, which is the 2D equivalent of the Z2 state. The difficulty in being data limited is that in this experiment, we could only get maximum 1,000 shots, so 1,000 projective measurements for a 256 qubit system. And if you think about informational completeness in tomography, you might realize that that's not enough data to reconstruct the state. So here's actually the energy, the expectation value of Hamiltonian, as a function of training, for the neural network trained on the experimental data. And I happen to know the ground state energy for my own simulations. And basically, you never get there because you don't have enough information in your data set, and then you start to overfit. So you can see the utility and the challenges with having limited data. One thing that came out of this experiment was if I combine and this is very technical, but maybe for the VMC people, if there are any, if I combine the loss function that's data-driven with a loss function that's variational, so if I believe I know the Hamiltonian, here's the variational optimization of the same wave function. And one thing I didn't mention was language models can be trained without data via the variational principle. So they're very flexible in that sense. So
this other, this f by phi is what some kind of some correlation functions, or
yeah, so that's just that's basically just
Fourier correlation.
it's looking at, yeah, I don't know why they're subtracting off pi 0, I forget, but it's basically just the structure factor for the Z2 state. Yeah. So you see it's brighter here because you have a bigger signal. Yeah. Anyway, my point again for the experts in some sense was that, you know, if I take data-driven models, if I initially train them with data and then switch the cost function to being variational after, and I do it at different time steps here in the green, I actually see a much more rapid convergence. So one of my pitches to you is that if you're doing variational Monte Carlo using one of these neural networks, it's very, it makes a lot of sense to pre-train these things on experimental data. You'll get much better minimum and a much quicker time than if you do the optimization purely from the variational case. Was that a question? Was that just a thumbs down?
No. Question of how to frame it, I guess. Why not just have both inside the loss function and
Great question.
both inside the loss function at the same time? Why not have a time when it switches?
Don't know the answer to that. If we reverse this, it doesn't work. So it's very important to train from data that's drawn from the target distribution first. And that has to do with the point for the non-experts here is that early phase training really, really matters in these models. So if you're training a model based on the target state, it's much better to do that first than if you're training it from, you know, you're trying to find the ground state of a Hamiltonian, which is in some sense not the target state at all, right? So I don't have an answer for that, but it's a fact that we've observed.
So just to make sure I understand, so you have a machine which you think has put the quantum system in its ground state. You're making measurements. You're getting some limited samples from that.
Yep.
Training to get like a rough starting point for the
Optimize it. Yep.
Hopefully some gradients for the optimizer.
Right. And then we switch the cost function to variational with the same Hamiltonian, hopefully.
Yeah.
And so again, my pitch to Misha is just give me clean projective measurements on complicated models, sign problematic or some difficult models where VMC doesn't work great. But your data will help drive me to the global minimum much faster than if I just do conventional variational Monte Carlo. So it's a really hybrid thing that I think is really promising in the future. I go, what? You waited for this whole time for a transformer. So here it is. I call it Rydberg GPT. So this, again, I'm doing this as a function of my time. Things I did first, restricted Boltzmann machines, recurrent neural networks in 2 dimensions. So we basically transitioned all of our architectures to this encoder-decoder architecture of GPT. This is literally the same as the GPT-4 or something like that. On the left-hand side is the encoder, and on the right-hand side is the decoder. And I've simplified that attention thing that I had on previous slide. Now my prompt isn't, produce me a picture of a stormtrooper. It's the Hamiltonian and the parameters associated with the laser detunings and the Rabi frequency and the interactions, and I even have a temperature in there. That's my prompt. The input of the decoder is the sample from the device. Okay, so the projective measurement, given that Hamiltonian that's been prepared, and then the output of the decoder going through all these layers up here is that sequence of conditional distributions which defines my wave function, okay? So the encoder-decoder model is super interesting because what you can do is train the thing and then hope it generalizes to different prompts, just like GPT-4. And what we find is this works really great. We haven't published it yet, so I'll give credit to David Fitzek from Chalmers, who came and coded this up, and a couple of my students, Yihong and Gibre. So here is just the expectation value of the Hamiltonian as a function of detuning for, a prompt, right? So it's the Hamiltonian parameter delta I'm changing. And here's the energy calculated from the output. And I've only trained it on the points where the red arrows occur. This is going through that Wilson-Fisher fixed point. And the blue is the output of Rydberg GPT after training, given different prompts. So really out of distribution, probability distributions. And I have the quantum Monte Carlo ground truth, and you can see it's a perfect match. And I have previous versions of this where we had, intermediate stages of training where it was a huge mess. So the GPT, in this case, the transformer, I believe, really systematically improves with the more data and the more parameters and all the more compute and everything you put through it. So we're really at the point now where I have language models that I can query with different prompts that give me insight into regions of phase space for these experimental devices, which the experimentalists themselves haven't explored yet. So I hope it's a great tool going forward for experimentalists.
Sorry, could you please explain again what is the prompt here?
The prompt is the Hamiltonian parameters. Omega, delta, the interaction matrix, and I have lattice spacings and I have the temperature.
Just several numbers.
Yep, the Vij is actually a matrix, so I needed an additional graph neural network to embed that. But if it wasn't a long-range interacting Hamiltonian, it could be a finite set of numbers. Yeah. Prompt is the Hamiltonian. What is the ground state distribution? Okay, so that's the last thing I really wanted to show. I have tons more applications in case I ran out of or had too much time, including quantum error correction. Is Dangtong Li in the audience? You have a CS student here at Yale who developed exactly the same architecture for decoding the surface code and has a great paper on it. So just wanted to, I believe the utility of language models, and this is my last slide, goes beyond what I just showed in terms of Hamiltonians and prompts. And really, you could input all sorts of things and get output distributions, including if I have a syndrome and I want to output the probability distribution of the error chain, almost obvious, right? Google, my slide that I just skipped over was Google's done this now in their devices. They're using a GPT-like model. It's not a transformer. They have actually an RNN, but they're using language models now as their decoders. So all of you kids, working on quantum error correction, just forget it. AI is taking over. But no. So that's it. LLMs are, I think they're remarkable and they're scaling into the macroscopic scale. And by doing so, demonstrate emergence. We can build our own LLMs, and I would encourage us to do so right from scratch. We should do it from our own data sets. Forget scraping the internet for stormtrooper pictures. Let's build these things off of the data that we produce in physics labs. And if we build them correctly, they'll be incredible tools. And I imagine a quantum device giving me shots, building a language model. I can interpolate if I have incomplete data, which is what the atoms give me, really incomplete distributions. But I can also extrapolate through like a prompting mechanism or an encoder-decoder type architecture to explore parts of the quantum computing phase space that are impossible to do experimentally or very costly to do. And so I think this is all possible. All of these things are possible. We know how to do it. We would love to scale these things to observe non-trivial emergent phenomenon like superconductivity or something like that. But I think the question is, it's an economics question also. Can we afford the GPUs? Can we afford the training? Should we afford the carbon output of these, training procedures and so on? So I think it's a really interesting time. If you want to read more of our crazy perspectives on this, we just put a perspective paper out in Nature Computational Science. Thank you for your attention.
Okay, thanks, Roger, for a really inspiring talk. Guess we have some questions some time for questions.
So in the language world, obviously, there's the foundational models are often they have huge benefits to transfer learning, right? So you build a super expensive model, and then I can fine tune it on my stupid data set myself, and it didn't cost me anything. Is there potential for that here? I didn't quite.
Right. So So what I'm building is still the foundation models. We're still building models. Instead of the foundation model being trained on internet data, I think my point, I didn't want to use the word, but we should be building foundation models on physical data.
And is that then something I could use, and my cost payment, you would have paid the fixed cost, and I'm.
Right. So you only have to train the foundation model once. Yeah, that's exactly the point. So you can take an existing foundation model and tweak it for certain tasks, obviously. But my argument is if you really want to build one that's relevant for some of these core challenges in quantum computing and so on, I don't think we should be using natural language models scraped from, Wikipedia. It makes a lot more sense that we start the foundation models based on physical data, even if it's imperfect. But if I want to build a foundation model for a neutral atom quantum computer, we have the data streaming out of these devices all the time now. So it makes sense to build those foundation models with the data that we have. And it's a one-time cost for training, like you say, and in the future, we can tweak these things or align them or whatever we do with conventional models. Yeah. Thanks. Great question.
Oh, it's okay.
You got to use the mic because I forget to repeat the question.
That's okay. Yeah, this is actually not so much related to the quantum simulation thing, but as much as you're talking about Google's labs that are working on AI applications and this sort of things. Do you know why they're using just like basic kind of vanilla RNNs? In this case, at least it was suggested based off of what you're showing there. Yeah. Like, why is there any advantage to using that over a more complicated model? Is this mainly because they could just scale and like that would be easier to train in that situation, or is it for another reason that I'm not quite understanding? Yeah.
So I don't know the answer, but I can guess. So two reasons. Number one, I think if your models are small, RNNs still work just as good as transformers. And so far we're still, the data set sizes and everything, and the number of parameters is still small. My transformer model has 66,000 parameters. It's nothing compared to GPT-4. The second reason is inference is cheaper in an RNN. It squares as n. So if you have n qubits, you do that inference step in n, whereas I believe it's n squared in the transformer. So is that right? I think that's right. So the inference cost is lower. As long as they work, as long as you can train them, the RNN inference cost is lower, I think.
Got it. Thank you. Yeah, that makes sense.
Thank you. Great talk. Just kind of a naive question going back to the basic classical large language models. So one of the trends is as you go from GPT-3 to GPT-4 is that behaves better. And I think there was a comment that I might have misheard, but about, you're throwing more parameters at the problem and counterintuitively it's working better. But isn't the problem that we're trying to solve like a really high dimensional thing with many degrees of freedom? Like, how do we know how many parameters really should be required to, fit the data well?
I mean, we had exactly the same question as we did the Rydberg version. How big should this model be? So if you look at the number of parameters here, 10 to the 3 versus 10 to the 9. I don't think there's any connection between these numbers and sort of the information content of the data set in the language case. It's just the fact more parameters work better. And the transformers are easy to increase the number of parameters in. So you just kind of, but I mean, I think this in some sense is the non-answer to your question. With more parameters, it's observed that these models get better performance on the same number of data processed in them. So the bigger models, counterintuitively, because you think they overfit, right? Counterintuitively, they work better than smaller models here.
Unless they're still sparse. Like suppose the biggest models you can make are still guessing, basically.
Well, I'm sure they're going to be sparse in the quantum context where our Hilbert space is 2 to the n, which is exponentially growing. So something I didn't mention was why did we start using neural networks way back in the day? We hope that they were more efficient parameterizations of the quantum wave function than some naive parameterization. And so in our case, you're certainly right. They should be sparse, or hopefully they're sparse, yeah. But no, sorry for the non-answer. I don't know. I don't know many things.
Okay.
Oh, one online. Online question?
Hello. Could you go to the GPT model you developed by yourself? It's like the Roger GPT or something. Could you go to that slide?
Did you change the Robert, your own model?
Say it again.
He wants you
Go to Rydberg.
Oh, you want to go to Rydberg GPT?
Yeah.
Patent
Oh,
pending.
yeah,
patent
that's fine.
pending. Just kidding.
Yeah, thank you. It's a really amazing idea. I just want to make sure if I understand the concept here. So the input on the right branch on that one. So in the training, that will be at, for example, at t-1 step, and you are predicting t step and try to calculate the loss. And during the prediction, it will be whatever your model is generating in the previous step. Is that correct?
I'm not sure I got it. So are you asking about the sequence?
Like what's the input on the right branch? What
On
is
the right
it?
branch, oh, the input on the right branch is a projective measurement from the quantum computer. So these are the qubit states. And I have a sequence here because this is an autoregressive model. Oh, I don't know if you can see my mouse, sorry. Here, online. So yeah, I mean, you don't need the sequence in principle. It's just there for illustration. But I have a Hamiltonian and I get 100 shots out of the computer. The shots go into the right-hand side. And the output is the wave function or the joint distribution.
I see. So it is coming from the measurement, or it is
Right.
it's
This
like
is the measurement.
Okay.
The lower right is the measurement. Yeah. That's the data you would get from the device.
I see. But also the left-hand side, those inputs, are these also from the measurement, or they are from like?
No, the left-hand side is the experimental parameters that you set, the laser, the knobs on the lasers, you know. So you build your quantum computer and it has, you know, this has a Rabi frequency, a detuning, an interaction matrix. Yeah, you're right. I don't know why it's square there. I guess because the interaction matrix is square or something. But yeah, so this is, the prompt is the experimental knobs.
I say, and so during the generation, instead of during the training, you only need the left side input, not the right side, right? Or you still need the right-hand side?
During training, you input everything in the bottom. You're matching a prompt to the instance, prompt instance. You put them both in. And then you're training through some complicated procedure, right? And the output is just the joint distribution at the top. Again, this is the original setting where I have binary data, and I'm trying to learn the distribution that underlies the black box, which is really the prompt.
I see. Okay, yes, thank you very much. I really love this talk. Thank you.
You're welcome.
Okay, no more questions. Let's thank Roger again.
Thank you very much.